Are you seeing my screen? Oh, okay. Sometimes the focus of the paper is the chemical, and trying to synthesize this chemical because it's a important chemical. And so what we're going to do is, our results are so short, we're going to combine this with discussion. So we're going to call this results and discussion here. And these results we'll put later. What we're going to do is, initially, who are we going to convince? Like, one of the questions I might get asked is, how do you know those crystals are what you think they are? And what's the purity? Is that 100% pure crystals of that, or what? And so probably the easiest thing is just to start from the beginning with the synthetic method. And so we're going to just talk about the synthesis. So in the synthesis, we had the first step, which is step one, or what's called reaction one, maybe. You don't have to label it like this. So in the first step, maybe this is a little bit redundant. Maybe we don't need this. But anyway, this is a rough draft, so I'm not going to worry too much. We'll clean it up later. So in the first step of the synthesis, chromium 6 in dichromate chromium 6 in dichromate was reduced to chromium 3 ion. So what did we use to reduce it? Yeah, so maybe we'll just say that by using oxalic acid. Something like that. Is that it? It could be, but what we're going to do is we're going to add some more details in here. One of the details is why oxalic acid. Another one is why do we go from 4, or not 4, why do we go from 6 to 3? In other words, why didn't we go from 6 to 4? Or 6 to 5, or 6 to 2, or 6 to 0? Why did it go to chromium 3? And so that might be a question. Yes. And so somebody might know, so what we should do is we should research, do a little bit of additional research, like maybe we'll go and look at some chromium chemistry on Wikipedia. And maybe we should read a little bit about chromium here. And one of the things in Wikipedia, in the data section over here, is the oxidation states. The ones that are in bold are the most common oxidation states. And so when you see this, chromium plus 6 is a common oxidation state. It's bold here. And what else are common oxidation states? 2 and 3. So it makes sense that if we're going to reduce 6, we're going to reduce it to either 3 or 2. Now, the question might come up is, how do you know you reduced it to 3? Could it have gone to 2? So somebody might ask you that, and if you don't address this, then the referee is going to write this as a question and ask you to address it later on. And so it takes more and more time to get it published. But why did it go to 3 and not 2? That would be a legitimate question. Do you know?
Would be the amount of electrons that oxalic could.
Yeah, oxalic could, but you just add more oxalic. So if you need more electrons, just pour in more oxalic acid in there. Shouldn't that take it to +2? In fact, we did add, an excess of oxalic acid. So why didn't that take it to +2? And so, a question like that might come up, and do you have an answer for that? Maybe we should put something in the paper in case somebody were to ask, why 3? But we need to understand a little bit more about chromium-3 and chromium-2. So let's read some more about chromium. And so reading more about chromium, let's just read the Wikipedia entry, which is pretty good. Chromium metal is valued for its high corrosion resistance and hardness. That's chromium-0, the metal itself. And we could have reduced it to chromium metal, but oxalic acid probably wasn't enough for that. We didn't see any evidence of metal. A major development in steel production was the discovery that steel could be made highly resistant to corrosion and discoloration by adding metallic chromium to form stainless steel. And so stainless steel is compared to regular steel. Regular steel rusts pretty easily. Stainless is hard, more difficult to rust, but there are many different formulations of stainless steel. So not all stainless steels are equally resistant to rust. Like the 400 series stainless steel can rust, but the 300 series stainless steel isn't going to rust. Stainless steel is a mixture, and there's lots of different mixtures in it. Stainless steel and chrome plating. Chrome plating is when you electroplate with chromium. Together comprise 85% of commercial use. Chromium is also greatly valued as a metal that is able to be highly polished while resisting tarnishing. Polished chromium reflects 70% of the visible spectrum. So 70%, that would make a decent mirror. So you should be able to get a mirror finish with the chromium, and almost 90% of infrared light. The name of the element is derived from the Greek word, chroma, meaning color, because many chromium compounds are intensely colored. Okay, then they talk about industrial production of chromium. They get it from the ore, chromite ore, and then they process it. So this is about processing the ore to make chromium. In the United States, trivalent chromium-3 ion, is considered an essential nutrient in humans for insulin, sugar, and lipid metabolism. However, in 2014, the European Food Safety Authority, acting for the European Union, concluded that there was insufficient evidence for chromium to be recognized as essential. So in the U.S., trace amounts of chromium were thought to be essential for good health. And I guess there's some debate about this, so you can read, the countering argument for this by hitting these footnotes. While chromium metal and chromium-3 ions are considered non-toxic, hexavalent chromium-6, is toxic and carcinogenic. So, what do you think is more common in nature? If chromium-3 is an essential element for good health, then in nature you must be able to find chromium-3. So chromium-3 must be the stable form of chromium in nature. Not only that, it says it's non-toxic. If chromium-3 is non-toxic, is it very reactive? No, it's got to be pretty stable. And so we would suspect chromium-2 is more reactive, less stable than chromium-3 based on this data. We can look it up, chromium-2 versus chromium-3 ion. and C. And when we do that, the data seems to support that chromium-2 is not as stable. The other thing is, we can look at the color. The color of chromium-3 is green. The color of chromium-2 is blue. What color was it after the oxalic acid reduction? So the color after the oxalic acid addition was probably black. And so something else is going on there. Something else that's going on there is oxalic acid was also used to chelate the chromium. And that's going to change the color. And so the color is not really going to help us. So what we might say is that in the first step of the synthesis, chromium-6 in dichromium was reduced to chromium-3 ion using oxalic acid. Oxalic acid was chosen. Well, actually, let's put in the equation here. So do you recall what the equation was for this? We're just going to write the net ionic. It was CR2O7. Actually, I'm just going to write it out and then I'll do the subscript later. So we have our dichromate plus oxalic acid H2C2O4 plus some H pluses, I think. And this produced chromium-3 plus CO2 plus H2O, I think. Is that right? And to emphasize, since we're writing a formal paper, I'm going to write in the states, even if it's aqueous. Normally I don't bother writing aqueous, but not everybody's the same, so just do it the long way. CO2 is a gas, and H2O is a liquid. All right, then I'm going to do the subscripts and superscripts. So, which is a bit of pain, but I usually just do all the subscripts together by highlighting and do Control Y. Control Y is just redo the previous command. And then the superscripts I'll do together. Hit the first one, and then the remaining ones I'll just do a Control Y, highlight and Control Y. I don't know if this is. If you have a better way, let me know. There used to be an alternate program that I used to use that had a simple keystroke for switching from superscript back to normal and subscript back to normal. But this doesn't, at least not that I'm aware of. So this is going to make 2 chromium-3s. What was the balanced equation?
8 H pluses.
8 H pluses.
3 oxalic acids.
How many oxalic acids?
3.
3.
6 carbon dioxides and 7 water.
6 carbon dioxide, 7 water. Thanks. And we'll call this equation 1. Or reaction 1. We can get rid of this reaction 1 here. We don't really need it. In the first step of the synthesis, chromium-6 and dichromium was reduced to chromium-3 ion using oxalic acid. So one thing we could say is why chromium-3? Well, we could say this, stable, because it's got to be stable. It's unreactive, that is, it's non-toxic and seems to be an essential element. So maybe that's enough. Chromium-6 is quite reactive, though, in dichromate. And so why did we choose oxalic acid? Oxalic acid, the reducing agent, was chosen for multiple reasons. What was the first reason that we used oxalic acid? One, is it a strong reducing agent or a weak reducing agent? Or something in between? How late do we go till?
55 or 420.
4:20? All right. Guess we have time. Actually, it's pretty weak. It's pretty weak. Oxalic acid, the reducing agent, was chosen for multiple reasons. It is a weak reducer. And will not react too violently with the... How strong is dichromate as an oxidizer? It's a strong oxidizer, right? Chromium-6. And will not react too violently with the strong oxidizer. Dichromate. Carbon in oxalic acid has an oxidation state of... What was the oxidation state of carbon in oxalic acid? +3. Carbon in oxalic acid has an oxidation state of +3. Making it relatively electron poor, as it can only lose one electron before it is completely oxidized. To plus 4. And carbon dioxide. So what we can do is we can try to make a little figure for the oxidation states, and then maybe make another equation for the reaction. So I'm going to do first the reaction. And so we'll take oxalic acid, H2C2O4. And then oxidize this to CO2 plus 2H plus. So I'll need 2 CO2s for this. Since I have 2 carbons there, I'm going to generate 2 electrons. So 2E minus. So that'll be equation 2. This will be aqueous. Those will be gas. The generation of carbon dioxide as a product was another reason to use oxalic acid. The CO2, carbon dioxide, effervesces out of the mixture and removal of this product when isolating the crystals was not necessary. So in other words, we didn't have to wash it out. We didn't have to filter it out. We didn't have to do anything extra to get rid of it. And that's a byproduct. That's a product we don't want. So let me go ahead and fix this. The final reason for using oxalic acid was that oxalate ion is required for the next step of the synthesis. So if you add in excess oxalic acid, we don't have to worry about removing it for the next step because we can go ahead and use that in the next step in the synthesis. So we'll talk about that a little later. Dichromate is a strong oxidizer due to the high oxidation state of chromium. Chromium-6 is the maximum oxidation state for chromium, making this species electron poor. And so what we'll do here is we'll add in another equation here for the dichromate reaction. I'm just going to copy this so I don't have to rewrite everything. So we're going to go with dichromate plus 14H plus, okay, if I have two chromium 6s and I need to form two chromium 3s, I need 6 electrons for that. So I'll have plus 6 electrons. This is going to produce 2 chromium 3 plus and 7H2O. So this would be the half reaction for that. So we'll call this equation 3. Care was taken. This was also in the experimental section, but we'll just go ahead and explain why care was taken when mixing these. Care was taken when mixing and vigorous reaction took place. And so the final thing is maybe we'll put in the oxidation states here. And so for chromium, it was plus 6, And then oxygen had a -2. It's dichromate. And then oxalic acid, hydrogen is +1. Carbon is +3. And the oxygen was -2. And so I'll just make a little figure here showing that. So let me copy the dichromate. Just paste it there. And then what I'm going to do is I'm going to make a little drawing here. Let's see. Pen works, but since you don't have a tablet, we can do the drawing like this. I'm going to insert a shape. Let's put an arrow in there. And so we'll draw an arrow from the +6 here down to the chromium, like that. And I'm going to clone this arrow. I'm going to clone this arrow by pushing Control-click, and we'll make a duplicate. And then we'll do some more cloning here for the oxalic acid. So the oxalic acid formula, I'm just going to copy this and paste it down here. All right, it depends on the audience. You know, the audience that this paper is targeting will be like Chem 1A students. So if your audience is scientists working in the field, then something like this is not necessary. You know, they'll know how to do oxidation states, so you don't have to show it. They can just see it themselves. But since our audience, they may or may not be that comfortable with oxidation states, we'll go ahead and do this, write this out. In fact, we probably should put this, because electron poor and electron rich is not defined in a dictionary, so we'll put that in there as well. But we're also going to do chromium 3, and so here I'm going to write +3 in CO2. CO2, carbon is +4, and oxygen is -2. And so I'm going to copy the chromium 3 here. Just need one of those. And then I'll copy the CO2 from up here. That here. And then I'm going to clone these arrows over here. Control-click and just drag it. Just the angle and length. And then I'm going to label this figure. Let's go this figure 1 and give it a name. I'll call it figure 1 oxidation states. Since some people will get, what the heck are you talking about? Electron poor, electron rich. Maybe we should have a little bit of explaining about what that term means. Otherwise, the referee might not be familiar with this terminology. Yes. The arrow, go to insert, and then shape, and then just pick the arrow. When I pick the arrow, then you click where you want the tail to be, and you unclick where you want the head to be. And then you can adjust the angle and the length by grabbing the circle. And then you can clone this. To clone this, control click the arrow and you can clone it. So I'm going to add a word or two about the electron poor and electron rich. So atoms with oxidation states close to or at the max, at their maximum positive oxidation state are considered electron poor and are typically oxidizers. Oxalic acid at +3 is close to the max. And relatively electron poor but when mixed with the strong oxidizer, dichromate, the electron, the last electron can be oxidized. It is a weak reducer. Strong reducers will have oxidation states close to or at their maximum negative oxidation state, making them electron rich. Now, electron poor and electron rich is a term I like to use, but it's not common usage, so I'm going to put these in quotation marks. The oxidation state carbon varies from -4 on the rich end to +4 on the poor end. For chromium, the oxidation state typically varies from 0 to +6. Chromium could go negative. We go back here on the Wikipedia. You see it goes to -4. These ones are going to be very rare. -4, -2, -1. We got chromium metal. Chromium metal, it's a metal. Metals typically lose electrons. And so metals become oxidized. So this reaction seems to make sense. If we look at it, the CO2 is it's maxed out here at +4. We can't oxidize it any further. So that gas was generated. The only thing is chromium 3. We don't have much else to go. If oxalic acid loses that electron, it's going to go to +4. And +4 is either going to be CO2 or carbonate. Carbonate's also carbon +4. And so one or the other. However, chromium, we have a choice. It could go to chromium 3, chromium 2, or chromium 0. And so that's why I spent a little bit extra time talking about that here. This reaction 2 is step 2, the reaction. So I might change this. The chromium ion, the Cr3+, is the chromium 3+ in the next step of the synthetic method was chelated by potassium oxalate actually this is was chelated by oxalate actually maybe let's say by the bidentate ligand oxalate or oxalato forming the octahedral trioxalato complex. trioxolide complex ion. So here you could hand draw this or do whatever you want. So leave some space open here. We can hand draw the reactions here. So it's chromium 3 plus. We had two ways of going about this. One way is, we attack this with one oxalate. And so one of the things is, why is it bidentate? Why isn't this tetradentate? Oops. So we could do this in 3 different steps, or it depends on how many drawings you want to do. And so you can see each oxalate makes a 5-membered ring. So we might put that in here. It was chelating by the bidentate ligand oxalate ion, forming where each oxalate binds to chromium, forming a 5-membered ring. A question might come up, why is oxalate bidentate? Why isn't it monodentate? Something like that.
Wouldn't you have to name it trioxolate chromium 3?
We could. Just call it, rather than call it trioxolide complex, we can just call it trioxolide chromium 3 ion. That's fine. Let me check something. let me add one more sentence here. Both oxalic acid and potassium dichromate, not dichromate, potassium oxalate supply the oxalato ligand for this Lewis acid base reaction. And so I just added both oxalic acid and potassium oxalate supply the oxalate ligand for this Lewis acid base reaction. So I'll just do one more drawing here. And so this is with potassium oxalate. And then we'll do with oxalic acid. And so with oxalic acid, we're going to have our chromium 3+. And it's going to be attacked by to form the same complex, but with these H pluses broken off. So we'll have to have 6 H pluses that are generated for this. Okay, so that's the next reaction. What we can add to this is a little bit more. In this reaction, two of the oxygen, 2 of the 4 oxygens act as an electron pair donor. Donating the electron pair to the acid chromium 3 ions. Forming a coordinate covalent bond. Because of the trigonal planar shape, the other 2 oxygens would point in the opposite direction, not allowing them to participate in the bonding. Since the two oxygens are separated by a 2-carbon chain, oxalate can act as a bidentate ligand without bond angle strain because of the formation of a 5-membered ring. This might be a little bit confusing and needs to be. Chelated complexes are typically stable. And difficult to dissociate or break apart. Go with their suggestion. So that's kind of the driving force for this. These complexes are typically quite stable. Usually when we form more bonds, things become more stable. But it also depends on the bond we're forming. Like the NO bond is not as stable as, even though it's a triple bond, it's not as stable as the N bond and the OO bond. Okay, is there anything else? Well, if we think of something else, we'll add it to this. No. Yeah. That's a good point. We need figure 2 here. We can call it chelation or formation of the complex or Lewis acid-base reaction. This one? Yeah. Okay, just one more step, one more major step. In the last step of the synthesis, well, maybe we'll start it off like this. Was this indented? For some reason, this got indented. I think I just forgot to reformat it after the abstract. It's all right. In the final step of the synthesis, solid and here we could use the formula. Well, I'm just going to copy the formula and paste it. Was formed using solvent exchange and metathesis. Metathesis is that ion combination. In this sense. Metathesis, you can have different kinds of metathesis. There's a more broad definition, but the definition we're using are just favorable ion combinations. Potassium salt Potassium salts typically are soluble, or maybe I shouldn't say typically. I said that potassium salts in general are soluble in water. Polarity of salts typically decreases. Solubility of salts decrease in less polar solvents. Such as ethanol. Ethanol is miscible in water. Making solvent exchange feasible by just adding more ethanol, just adding ethanol such that we end up with more ethanol than water in the mixture. This causes the ions to combine into a precipitate. product. And so here we can have another equation. And I think we're out of time. Yeah, we're out of time. So I'll have to continue this. We'll continue this a little bit at a time in the lab, but we have the main part of the paper down. So we'll just add some more words about the metathesis and then about the cleaning of the crystals, that is washing, and about the recrystallization. And then we'll just clean up all the language and grammar in this. Okay? Yeah, the drawing. You can show this step by step in more detail, or just show it happening in 3 steps like this for the drawing. Just some kind of sketch where we're showing this reaction, and then we'll do one more sketch. If we see a figure that we want to use off the internet or off some paper, we can incorporate that into our paper. So if you see a good figure for this that somebody has already made, then go ahead and copy and paste that into your paper, but make sure that you cite the source. That's fine. So in the metathesis, we're going to make crystals of this stuff. And so I was thinking, well, I saw a paper for the crystal structure. And so maybe there's a nice figure for the crystal structure of this. We'll take a look for that later. But since we're out of time for today, we'll stop here and then we'll take a look at the Le Chatelier's lab tomorrow, at the beginning of class. And we're going to continue chapter 15 tomorrow.